So good morning, good afternoon, good evening, depends on where you are in the world. So today we are here to attend the talk by Professor Paolo Crovetti from Politecnitico di Torino. Professor Sérgio Bumpi will be the session chair. But today we are here to listen to the talk by Paolo. So I give the floor now to Professor Bumpi to do the presentation of Paolo. So thank you, Paolo, again for accepting our invitation. Thank you also, Professor Bumpi, for accepting to be the session chair today.
Okay, thanks very much, Paolo. It's very good pleasure. Okay, we're very pleased in the Rio Grande do Sul CASS chapter to host you for this very distinguished talk. And let me say a few words about Paolo. He received the laureate degree summa cum laude from the Politecnico di Torino in Turin, Italy, in 2000, and a PhD degree from the same institution in 2003. He has been a professor at the same department of electronics and telecommunications. Currently, he's an associate professor, and he's also a senior member of IEEE. He's been known for many journals and international conference papers where he introduced very new ideas, and he has developed this idea and proposed this idea 10 years ago of the so-called digital-based operational transconductance amplifier. And he'll be sharing with us all the journey that he has traversed since introducing this concept originally that he invented back in 2013. So he's also a good friend of Brazilian researchers here. He has hosted Brazilian students in his lab, and we have good ties from Rio Grande do Sul in the area of circuit design and also Politecnico di Torino, with exchange of professors and postdocs and scholars. Well, without further ado, thank you very much again, Paolo Crovetti, for accepting this. It's an honor, a pleasure to hear to you in the next 55 minutes or so. Thank you.
Thank you very much, Sergio, for your introduction. Thank you also, Ricardo, for this invitation. I'm very glad to be here today to talk about the digital-based operational transconductance amplifier and its evolution over the last 10 years. Indeed, the digital-based OTA concept was first proposed in a paper appearing in the IEEE Transactions on Circuits and Systems in 2013, something less than 10 years ago. And in this talk, I will review the original digital-based OTA principle and its development over the past 10 years in the context of the evolution of the IC technology, design, and applications scenario of the same period. But before doing this, before accompanying you in this 10 years long research journey, I would like to acknowledge in this slide the contribution of several travel friends who have been involved in this exciting experience, starting from my present and former students and all the guys who have worked with me at the Department of Electronics and Telecommunications at the Politecnico di Torino, and to all the colleagues from all around the globe who greatly assisted and helped me in these years. So thank you all. Now let's enter into the technical content of this talk. I will start outlining the technology and application context of these last 10 years. Then I will introduce in this concept the trend towards digital-based analog processing. And in this framework, I will introduce the digital-based OTA, that is the subject of this talk. I will outline the evolution, the different solutions based on this concept in the last 10 years, and then I will discuss some future perspectives. Then I will draw some conclusions, of course. So let's start with the context. While discussing the global IC scenario in the last 10 years, the first aspect to be mentioned is the progress in the technology. We moved from 28 nanometer to less than 5 nanometer feature size with a dramatic improvement in the throughput of digital systems and also reduction in power consumption following the trend predicted by Moore's law that we know has recently passed. So I take the occasion to remember him in this talk. Then we have, from the perspective of application, we are assisting more and more to the explosion of the Internet of Things, that is the vision of the world in which integrated circuits are embedded in everyday life objects acting as nodes of a globally interconnected network. Then in recent years, we fostered by the increased computational power and by the increased availability of data, we are assisting to the development of artificial intelligence, computers which are capable to learn without being programmed, that also change the context of data acquisition and processing in a dramatic way. And we have also assisted to a strong development in biomedical applications, starting from low-cost wearables to pioneering drinkable and injectable biosensors according to the body dust paradigm. Okay, so what is needed from the ICs so that to meet the requirements of these applications? Well, ICs targeting the IoT and biosensing applications need to be tiny, from the cubic centimeter down to the cubic millimeter scale, so that to be placed anywhere. They need to be energy autonomous, operated by very, very small batteries or energy harvesters, which means in practice that the power consumption should be extremely low, in the low microwatt down to the nanowatt range. They need to be highly reconfigurable so that to consume power only when it is really needed. So they need to be operated in duty cycle or possibly event-driven mode. Possibly their performance needs to be reconfigured in a dynamic way so that to consume to possibly trade off power with performance depending on the available power. Last but not least, the cost of ICs need to be kept very, very low. So it means that the mainstream digital CMOS technology should be adopted for everything, but also that design costs need to be minimized, and also the design effort needs to be minimized. Well, in this context, we can say that these requirements are particularly challenging for analog integrated circuits, since they do not take advantage of scaling. There is no net area reduction for analog cells while moving to more advanced nodes, and on the contrary, in more aggressively scaled nodes, we have that the analog performance of transistors are typically getting worse and worse. As far as the power consumption is concerned, unlike in digital circuits, the operation at lower supply voltage does not bring any net advantage. And another important issue is that since traditional analog ICs need to be operated at a fixed bias point, it means that static power should be drawn from the supply for biasing even under zero input signal, when no signal is to be processed. Okay. Last but not least, analog ICs show a limited reconfigurability, required a significant design effort and time. Typically, they require a manual transistor level design and optimization, and a full custom layout that can be extremely critical, especially in extremely scaled technologies. Okay. In view of these limitations in analog IC design, we have assisted to a steady trend towards the implementation of analog blocks by digital intensive replacements in the last decades. It is sufficient to mention, for instance, that in 2004 the all digital PLL has been proposed. In 2010 the digital LDO has been introduced, and both these circuits have become quite popular in recent years. In this context, in 2013, I tried to follow a more radical approach. I started considering if we could possibly do without analog circuits at all. When asking myself if we can completely replace analog circuits by digital ones, the obvious answer is that we will always need analog circuits, at least in interfaces towards what is an intrinsically analog physical world. At this point, however, I started doing some considerations about the fact that if we are sure that we are living in an intrinsically analog physical world, well, we know that matter is made of atoms, which are discrete entities. We know that all fundamental physical quantities like the charge, electrical charge, the elementary electromagnetic energy are also discrete, are quantized. Okay, and not only the inanimate world proves to be discrete in nature, but also in animals and in humans, information is processed and transmitted in the form of discrete pulses. So in the end, maybe it is more correct to say that a discrete underlying nature is what is at the basis of our everyday life analog experience. Moreover, as shown by Shannon, we know that the information in itself is discrete in nature. If we have a band-limited noisy channel, no matter if we use analog or digital signals to transfer the information, the maximum amount of information that we can hope to transfer in this channel is limited, it's finite, and is a finite number of bits per second. Okay, but what is an interesting point to observe is that these results, Shannon's results on the discrete nature of information, do not apply just to computers or communication networks, but they also apply to any kind of information, including the information which is processed by sensors, actuators, interfaces, and any kind of circuits which are commonly regarded as analog circuits, like amplifiers, filters, voltage references, and so on. Actually, this idea suggested me the possibility to systematically rethink analog processing in digital terms. So what does it mean to rethink analog processing in digital terms? The idea is to devise true digital circuits which are suitable to process arbitrary band-limited analog input signals in form of voltages or currents to get arbitrary band-limited output signals at a fixed degree of accuracy. Using a true digital circuit, which means a circuit that processes information in the form of ones and zeros, that detect just two levels and process them in a synchronous or asynchronous way, including combinational or sequential logic, memories, and so on, and excluding in this digital circuit digital gates used as analog circuits, for instance, a CMOS inverter used as an amplifier. Okay, so this is the idea of digital-based analog processing. And it is in this framework that the digital-based OTA that we are discussing today was originally conceived. Considering that an OTA is the key building block of electronics and is used in especially in negative feedback configuration. The question is how to design a digital-based circuit which is functionally equivalent to an operational transconductance amplifier. As we know, an OTA is expected to provide an output current which is proportional to the input differential voltage, that is the difference in the voltage at the input terminals, and is insensitive to the common mode component of the input voltage itself. This is very often considered with a capacitive load, so that the output voltage turns out to be proportional to the time integral of the input differential voltage. So the question is, can we translate the function of an OTA into digital? Actually, this is not the first attempt to develop a digital-friendly implementation of an OTA. We can recall, for instance, the NAUTA circuit, which is an inverter-based topology that also operates at a high frequency, but also this solution is definitely not a digital circuit. In this circuit, inverters are used as analog amplifiers, and information is processed in the amplitude domain. So let's try to follow a different approach. Rather than starting from the small signal analysis, which is the typical starting point for analog circuit design, let's start from a behavioral description of the circuit, as we do for digital circuits. If we consider the output current to input differential voltage static characteristics of this circuit, if we assume that the transconductance tends to infinity, that cannot be achieved in practice but would be highly desirable in an OTA, we have that the behavior of this circuit can be described in a very simple way. If the input differential voltage is larger than 0, the output current is equal to the positive bias current. If the input differential voltage is less than 0, the output current is equal to the minus the bias current of the input differential pair. So looking at the output voltage, we can say that the output voltage is increased if the input differential voltage is positive, whereas it is decreased if the input differential voltage is negative. So this can be translated in a kind of analog behavioral pseudocode. If VD is larger than 0, then increase the out, else decrease the out. It means that we have to basically, in order to implement an OTA, we have to do two things. We have to detect if VD is smaller or greater than 0, and then we have to increase and drive the output increase or decrease the output accordingly. Now let's suppose to have two digital buffers with an ideal threshold behavior. If the input voltage is below the trip point, the output is 0. If it is above the trip point, the output is 1. And let's consider the digital outputs of these two buffers. Of course, we can have 4 different cases. These digital outputs can be 1, 1, 0, 0, 1, 0, or 0, 1. We can immediately observe that if the output corresponding to the buffer connected to the non-inverting analog input is 1, and the output of the buffer connected to the inverting analog input is 0, we can immediately conclude that the input differential voltage is larger than 0. In the same way, if we have 0, 1, we can immediately conclude that VD is less than 0. Based on this information, we can drive an output stage that can be a 3-state buffer, as in this case, so that, for instance, to turn on the pull-up device if the digital outputs are 1, 0, or turn on the pull down device if the digital outputs are 0, 1. Okay, unfortunately, this works only if out plus and out minus are either 1, 0 or 0, 1. When we have that the outputs of the digital outputs of these two buffers are at the same logical value, 1, 1 or 0, 0, it means we do not have any information on the input differential voltage. By the way, also in this case, the outputs of these two digital buffers provide useful information on the common mode input voltage. If we have 1, 1, for instance, it means that the common mode input voltage is above the trip point of the buffers, whereas if we have 0, 0, it means that the common mode input voltage is below the trip point. Based on this information, we can add a kind of common mode compensation signal to be added to the external inverting and non-inverting inputs so that to compensate the common mode of the external signals and make it closer to the trip point of the inverters as required to properly detect the sign of the differential voltage. So if we put together the common mode compensation network, the output stage, and these two simple digital buffers, along with the summing network that makes it possible to sum the common mode compensation signal to the external inputs, here we have the first digital-based OTA. Okay, if we simulate this circuit in a negative feedback configuration, we can observe that it actually acts as an analog signal. Here we have a voltage amplifier with a gain of 2, and actually the output is a sine wave that is with an amplitude that is twice the amplitude of the input signal. But if we look inside the circuit, we can see that the outputs of these two digital inverters oscillate between the 0, 0 and 1, 1 states, and during the transitions, depending on the input differential voltage, one of the two outputs crosses the trip point before the other. So in a short time interval, the outputs of this buffer are 1, 0, 0, 1, and the output stage is operated so that to increase, in this case, the output voltage. In this slide, you can see an animation that illustrates this concept. I have to thank my former PhD student, Pedro Toledo, for this animation. Okay, so for this circuit, the same analog performance parameters of a traditional OTA can be evaluated, so the frequency response, the gain bandwidth product, and it is very interesting to observe that such parameters can be expressed in terms of the typical parameters of the digital gates, like the delay, the propagation delay, or the rising falling times, and so on. A proof of concept prototype of this circuit based on off-the-shelf components was proposed in 2013 to validate the concept, and actually it proves the concept even if its performance is not outstanding. The next stop of our journey is in 2018, when the first amplifiers based on the DB-OTA concept have been demonstrated on silicon. In the digital-based OTA, the basic structure has been implemented in 180 nanometers by digital standard cells with using pseudo resistors for the input summing network. It occupies a silicon area of 1,400 square micrometers in 180 nanometers. And based on measurements, the circuit works at a supply voltage down to 300 millivolt. It is suitable to drive a capacitive load up to 150 picofarad with less than 3% THD. And what is more important, it draws just 400 picowatts power from the supply, thus achieving one of the best figure of merits among amplifiers operating at supply voltage below 500 millivolts. What is even more interesting, we have also simulated this circuit in 40 nanometer, and we have observed that when moving from a more aggressively scaled technology, the performance are expected to improve. That is something similar to what happens in digital circuits, and it's quite the opposite to what we are expecting in analog circuits. Okay. So now let's go ahead to 2020, when a new version of the digital based OTA that is known as DB-OTA has been introduced. Here, the main difference is that input summing network, which is not conveniently implemented on silicon by resistors, is replaced by digital elements, Mueller C elements, which proved to be suitable to implement the same function. The behavior of this circuit can be fully described in terms of a state transition graph as a finite state machine. And this circuit has also been demonstrated on silicon in 180 nanometers. It occupies an area of less than 1,000 square micrometers. It has a GBW it operates at 300 millivolt as well, with a GBW of 250 hertz, and also drives capacitive load up to 150 picofarad, with a power consumption that is here 2.4 nanowatt. Also in this case, the energy efficiency figure of merits are extremely competitive, and the operation of this circuit has also been proved in a pure harvested mode, that is using a very small photodiode, a very small solar cell to power the circuit. This circuit works properly even in a dark room with just the monitor of the PC on. More recently, in 2022, the digital OTA approach has been adopted also to design an amplifier targeting the specification of biosignal processing, like ECG, EEG, and EMG. Actually, the specifications are fully differential operation, bandwidth in the kilohertz range, and microvolt RMS range input referred noise. And actually, the idea is to take advantage of this digital-based approach to reduce area and power consumption also in these applications. Actually, for this purpose, digital-based approach has also been devised to control the common mode output voltage in this fully differential structure, and the input stage has been redesigned so that to meet the stringent requirements on the input noise. Actually, based on experimental results, we got that this DB-OTA operates from 0.3 volt VDD, draws 150 nanowatt power from the supply, and basically it meets the specifications of the application for which it has been designed. More research effort has been devoted to address the low frequency accuracy of the digital based OTA without increasing the physical dimension. So unlike the solution that has been proposed before, in which we had a much larger input stage, we have tried to find something different to improve the DC accuracy. Instead of using more conventional chopping or auto-zeroing techniques, a new digital-based OTA that implements the time multiplexed digital amplification concept has been proposed in the 2022. What is the idea? The idea is to achieve differential amplification and common mode rejection as in a digital-based OTA while using just a single digital buffer as a single-ended comparator. And multiplexing it in time so that to compare the non-inverting and the inverting input in two different time instants. So in other words, this circuit, the non-inverting and inverting inputs are first simultaneously sampled, then the non-inverting input is connected in series to the comparator and to a common mode compensation voltage source. The corresponding comparator digital output is stored in a register. Then in another time interval, the same operation is performed for the inverting input, and the digital corresponding comparator digital output is stored in another register. Then if the digital values corresponding to the non-inverting and inverting input are different, the output voltage is updated as in the digital base OTA, so it is increased or decreased, while if the two digital values have the same logic value, the common mode compensation voltage is either increased or decreased accordingly. This principle, actually, it can be also observed that based on the sequence of the states of this controller, a digitized version of the output is also immediately available. So this circuit implicitly performs analog to digital conversion as a byproduct, just to say. This principle has been implemented in 180 nanometer, taking advantage of switched capacitor techniques. In particular, the floating voltage source for common mode compensation is implemented by a capacitor, and the core digital logic of the circuit is implemented in standard cells. This amplifier has been fabricated in 180 nanometer, occupies less than 0.01 square millimeters. It operates with a power supply ranging from 0.2 up to 1 volt with rail-to-rail input and output swing, with a clock frequency ranging from 28 kilohertz at 0.2 volt up to 15 megahertz at 1 volt, which corresponds to a scalable gain bandwidth product ranging from 70 Hz to 40 kHz, and the power consumption ranging from 600 picowatt up to 9.6 microwatt. If we look at the performance at 400 millivolt VDD and 50 kilohertz clock, the DC gain is about 40 dB. The gain bandwidth product is 120 Hz. The open loop input referred noise spectrum reveals an in-band noise power spectral density of just 1 microvolt per square root of hertz, and you can see that thanks to the proposed concept, the 1/f noise is also inherently suppressed. Moreover, based on multi-die measurements, it can be observed that the DC accuracy, the input offset voltage, is in the order of hundreds of microvolts, in spite even if the minimum size standard cell, almost minimum size standard cell, is used as in the input stage. Compared to the state of the art of low frequency, ultra low power DC and AC coupled sensor interfaces, the front end based on this digital amplifier achieves the smallest normalized area, the widest power supply voltage range, and down to the minimum supply voltage, and operates at the lowest power among the DC coupled analog front ends, thus validating and proving the effectiveness of this technique. Going ahead, we have also explored the possibility to adopt the digital-based OTA concept in flexible XCO semiconductor technology. This has been done last year. This technology is very interesting since it enables the integration of transistors with decent performance on bendable, environmentally friendly substrates at very low cost. But from the designer's point of view, this technology has also several important limitations, since it is not suitable to the integration of complementary devices, as a coarse feature size, and achieves a low operation speed compared to mainstream silicon technologies. So we explored if taking advantage of the digital-based OTA approach, we can overcome these limitations. We have implemented a digital-based OTA using only NMOS transistor, and we have validated it by post-layout simulations. The structure is quite similar to the original digital-based OTA. Based on post-layout simulations, the proposed OTA operates at 3.3 volt power supply with a common mode input range of 1.4 volt, with the bandwidth in the order of 100 kilohertz, 36 dB DC gain, and power consumption in the order of 113 microwatt. This performance, of course, they are not competitive in absolute terms, but in the landscape of flexible operational amplifiers implemented in flexible technology, are quite competitive. In particular, this is the circuit which operates at the lowest VDD with the lowest area, and also achieves among the best figure of merits in terms of energy efficiency. Of course, they cannot be compared with the equivalent in a CMOS. By the way, it's a quite significant result. In a very recent paper, we also explored the application of the digital-based OTA in potentiostat-based electrochemical sensor readout. Actually, let's recall how traditional potentiostat works. For instance, this is the kind of circuitry which is used to monitor the glucose concentration in the blood. It is made up of an electrochemical cell that has 3 electrodes, the working electrode, the reference electrode, and the counter electrode. While the working electrode is normally grounded, the potential of the reference electrode needs to be basically fixed to a constant value by driving the counter electrode, and without drawing any current from the reference electrode in itself. This is normally done using a closed loop or operational amplifier that is connected in a negative feedback configuration. And depending on the characteristics of the electrochemical cell, we have that the current that is drawn at the output of this amplifier turns out to be proportional to the concentration of the analyte that we want to detect, in this case, the glucose. Actually, in order to sense this current in traditional analog implementations, we need another circuit based on other operational amplifiers or something equivalent. Our idea is to use here a digital-based op-amp to implement a potentiostat. Okay. Actually, what we have done, we have designed a new digital-based op-amp based on a floating inverter input stage, which operates synchronously. And another advantage of this solution is that it operates as a traditional potentiostat. Moreover, since the basically the charge is delivered at the output in the form of discrete current pulses, by just counting the pulses that are applied to the output, we can immediately estimate the current flowing in the counter electrode, that is the concentration of the chemical that we want to detect. So we can say that this thanks to this approach, this potentiostat has an inherently digital output, provides an inherently digital reading without needing any further analog to digital conversion. Actually, the proposed approach has been adopted to design a miniaturized direct digital sensing potentiostat for glucose monitoring. It has been validated by post-layout simulations in 180 nanometer CMOS. In this technology, it achieves the smallest area, just 460 square micrometers. It operates at the lowest supply voltage, 0.4 volt, with the smallest power consumption, just 4.7 nanowatt. It also achieves a good linearity, is rather tolerant to process voltage and temperature variations, provided that it is properly calibrated. By actually, the calibration is also needed in more traditional approaches. So after this overview of the applications, the different evolutions of the digital-based OTA in the past 10 years, let's look at the future. Let's see which are the perspectives, what are the current research challenges. While the performance of the digital-based OTA has significantly improved from the first prototype in the last 10 years, especially thanks to the adoption of the time multiplexed digital differential amplification, and it proves to be already valuable in many IoT sensor nodes, in application in IoT sensor nodes and biosensor. We can say that there is still a gap between the digital-based OTA and traditional analog solutions operating at nominal supply voltage, let's say about 1 volt, in terms of DC gain, bandwidth, and this is, of course, a topic that needs to be addressed in further research. Then other research directions are oriented to the application of the digital-based approach in specific sensor readouts, for instance, bridge-based sensors, as well as in A to D and D to A converters. This is a topic that is currently being explored in my research group. And last but not least, the other perspective, the other open perspective, looking beyond the CMOS, is the adoption of the digital-based OTA approach to implement analog functions in emerging technology originally conceived for digital processing. We have already started with flexible organic substrates, but possibly the approach can be extended to other beyond the CMOS technologies like spintronics, optical computing, and also, why not, quantum computing as well. Okay, so I have now arrived to the conclusions of my talk. So summarizing, I have discussed the evolution of the digital-based OTA in the context of the technological and application landscape of the past 10 years, starting from the basic principle and the operation of the digital-based OTA, to conclude with the derived topologies and their applications. I have also discussed some open questions and present research perspectives for this technology. So I thank you for your attention, and I take this occasion to thank again all the guys in my staff and all the people all around the world who worked and contributed and helped me working on this topic. Obviously, I am at your disposal now, but also offline for any questions and for any further details on this technology. So thank you very much for your
Thank you
attention.
very much, Professor Paolo Crovetti. Very good talk. We are really, excited to entertain questions now. People in the audience, if you are, online now at YouTube, you can ask questions. Jorge Guilherme already, said here, it's a great talk. And he has a question for you. Jorge Guilherme is asking, what can be the maximum bandwidth for this type of block? He called this digital OTA, as a block. What can be the maximum bandwidth? Thank you, Jorge, for your question.
Thank you very much for this question. Actually, this is something that we are still exploring. What could be the intrinsic, if there are, and what could be the intrinsic limitations of these technologies. Actually, what we can say for sure is that the main advantages in terms of power consumptions are observed at low frequency, in correspondence of what is known in digital circuits as the minimum energy point. And actually, most of the research activities have been focused so far in this area. So actually, what is to be done is to explore also the high frequency capabilities of this approach. To be honest, when operating at nominal supply, we have observed that it is not difficult to achieve performance which are comparable to the baseline analog implementations, possibly without those significant advantages in terms of energy efficiency and power consumption. By the way, a gain bandwidth product in the order of megahertz, tens of megahertz, is absolutely achievable. We have not pushed towards the actual limits, but actually I think this could be an interesting topic also for further research. So thank you for your question.
Okay, I have a question regarding the implementation you did in the flexible substrate, IGZO. it seems like your average measured gain bandwidth product was about 86 kilohertz, and with a average DC gain of 36. Is anything that's intrinsic to that technology that made this DB-OTA better, slightly better at the lowest VDD than the one that you did at CMOS at 0.4 volts?
Yes, actually, it is not concerning energy efficiency and the power consumption at all. I don't think it is better than what we did in CMOS. Actually, what we did in CMOS is much more competitive compared to other silicon solutions. By the way, the main difference is that the circuit is operated at 3.3 volt. So actually, the higher bandwidth, the higher gain bandwidth product is basically related to that. Actually, due to the limitation of the IGZ-O technology, we cannot scale the power supply voltage so easily as we have done in CMOS. So in the end, we demonstrated this circuit just at let's say the nominal supply voltage for that technology, that is 3.3 volt. So this is basically the reason. The same results in terms of gain bandwidth product, as I mentioned before while answering the previous question, can be easily achieved in CMOS while scaling up the supply as well. In 180 nanometers, operating the circuit at 1.8 volt, we can easily achieve more than 1 megahertz gain bandwidth product. By the way, in these conditions, the performance in terms of energy efficiency and power consumption are not that competitive compared to other solutions in CMOS working at the same VDD.
Okay, we understood. So it's very important to know that you push it down this in the DB-OTA, push down the limits of scaling towards the maximum energy efficiency, and you have proven a very good energy efficiency. But if you go to closer to nominal VDD voltage, your digital operation, full swing, really, taxes or impairs the energy efficiency, let's say.
Actually,
so maybe the audience here will be interested in to know where is around which VDD is the crossover point between a top energy efficiency and a very good energy efficiency that beats the conventional OTA. At which VDD there is this crossover of energy efficiency that the large signal operation of the DB-OTA kind of starts to lose in energy efficiency figure of merit.
Yes, actually, we can say that the energy efficiency of any consideration on energy efficiency on the digital-based OTA can be closely related to the operation around the minimum energy point. That is the same concept that is normally adopted when discussing the best energy efficiency performance of digital circuits. So when operating a supply voltage close to the minimum energy point, that is in plain CMOS in the order of 300, 400 millivolt, this is actually when at least the first and the basic digital-based OTA gives the best in terms of energy efficiency. Actually, we have also to say that several solutions like the switched capacitor-based time multiplexed solution are probably less constrained to this concept, even if they are also mostly based on digital circuitry. processing is basically made digitally. So actually, the energy efficiency performance also of this solution is closely related to the digital energy efficiency of the circuit.
Okay, thanks, Paolo. There is another question by Jorge Guilherme. He wants to know how about the control of the offset voltages? What are the impacts of the offset? I think he's
actually
talking about he is leading towards conventional architecture, but he wants to know about how to control that.
If we consider the conventional architecture, we have to say that the offset is actually a problem, in the sense that using very small geometries and with all the limitations that can be expected in matching, in the first versions, in order to tackle with the offset related to mismatch, what has been done is to add basically a calibration network, so that to reduce offset. By the way, I think that the best solution is let's say it's a kind of analog approach to reduce offset. By the way, the digital based approach is the one that has been adopted for the time multiplexed digital differential amplifier. In this case, since we are using the same element multiplexed in time between the non-inverting and the inverting input, this solution is inherently offset free, and its operation is not related to mismatch. Actually, in that specific case, we used as a single-ended comparator a standard cell digital buffer with a strength that is not the minimum, but is very close to the minimum, and we got a measured offset voltage, RMS offset voltage, that is in the order of 100 plus minus 100 microvolts. Okay, we could possibly investigate, and we possibly can even further improve this figure. So I think that this is the most promising approach to cope with the offset.
Okay, well, I think that we are about already 1 hour in the seminar. I would like to thank you very much, Paolo Crovetti, for sharing this excellent lecture. I know there are many other things to say about this. You have been working on, the same mostly digital concept for, DAC converters, digital to analog, and with that we can have an A to D converters. There's much to be explored and said about the subject, and we know you have pioneered this concept, and it's coming to fruition in this age of IoT, nanowatt level, sub-microwatt, imperative type of analog design. So I congratulate you and your group, your collaborators, and on behalf of the Rio Grande do Sul CASS, Circuits and Systems Society chapter, we thank you very much for coming and sharing this excellent talk with us. Thank you very much.
Thank you very much, Sergio. And thank you, first of all, for your invitation to give this talk. I am very glad, and thank you all for attending. I am very happy to share with you. I am, as you know, Sergio, I am very glad also to have contacts with Brazilian people. I have had very good cooperations, and I'm very, very happy about that. So I would like to thank you all for this invitation. Thank Ricardo, and I'm very, very happy of this opportunity. Thank you again.
Okay. Thanks. So see you all chapter members in the talk in 2 weeks from now.
Yeah. Okay. So thank you very much, Paolo, for the excellent talk. Thank you, Bumpy, for sharing the session.